Okay, so now we're going to get into redox reactions. As I said before, redox stands for oxidation reduction. And what we're going to look at here is how do we identify a redox reaction occurring. Now, first we have to define what we mean by oxidation and then reduction. And as you can see here, oxidation occurs when the oxidation number increases, and that corresponds to a loss of electrons for an atom. And reduction occurs when the oxidation number decreases, which corresponds to a gain of electrons by an atom, right? And what you'll find is that in every single redox reaction, you must have simultaneous loss and gain of electrons. You cannot have one without the other, right? If something loses electrons, then those electrons would have to go somewhere. So if something is undergoing oxidation, then somewhere in the universe, reduction must be taking place, all right? So to give you a simple example of this, if you look at this here, this is showing you a reaction. Now, what you're looking at here is a picture of a cylinder with a solution known as copper 2 sulfate. And in that cylinder, you see a coil here, that's magnesium coil, right? And there's a reaction that is taking place in this system right here. In fact, let me see if I can write up here. Hold on 1 minute. I think I prefer the black color. Okay, so basically the reaction that is taking place is copper, Cu, solid, plus, I'm sorry, this should be CuSO4. Let me scratch this out. This should be, let me do it up here. CuSO4 aqueous plus magnesium solid to give you MgSO4 aqueous plus Cu solid, all right? Now, the thing about this is that the color, let me bring this here, the color of the copper 2 sulfate is blue, and the color of the magnesium sulfate is colorless. All right? So if you look at what's happening in this picture right here, you see that the blue solution is clearing up as the reaction is taking place, and over here the solution has become, you know, less blue and colorless, right? And the reason why that's happening, of course, is because the copper 2 sulfate is reacting, which is blue, to form the colorless magnesium sulfate. Now, this here is the molecular equation. If you remember when we talked about precipitation reactions and so on and writing down the net ionic equation, we made a distinction between the molecular equation, the ionic equation, and the net ionic equation. So what I'm going to show you now is the net ionic equation. I won't go through all the steps that I would normally go through to get to the net ionic equation. I'm just going to write down the final result, which would be Cu2 plus aqueous, and the state symbols are very important. Do not neglect to include the state symbols, plus magnesium solid to give Mg2 plus aqueous plus Cu solid, all right? So this is the net ionic equation that is taking place, right? This is the net ionic equation that is taking place, right? So the copper 2 plus is undergoing a change to form the copper solid, and the magnesium solid is itself changing to magnesium 2 plus. Another thing I want to mention here is that in addition to the fact that the solution is clearing up, you'll see the deposits, some flaky deposits on what is left of the magnesium over here. That would be the copper solid that is being formed in the reaction. Okay, so this is where the terms oxidation and reduction becomes important, because if you notice, there's a change in the oxidation numbers of the different species involved. In the case of the copper 2 plus, it has changed to copper solid. The copper solid has no charge. Let me make sure I make a note of that. So there's zero charge right here, right? So as far as the copper 2 plus is concerned, going from copper 2 plus over to the copper, there is a gain of electrons. And therefore, we say that reduction has taken place because the copper 2 plus, its oxidation number changes from +2 to 0 over here. All right? So that's the reduction. And at the same time, you have the magnesium, if I can see the pointer here, it's undergoing a change as well, right? Because the magnesium has changed from 0 to +2. In other words, it has lost 2 electrons. And therefore, we say that oxidation is taking place as far as the magnesium is concerned. All right? So this is a simple example of the redox process. So just to recap, in the case of the copper 2 plus, its oxidation number is reduced from +2 to +0 as the reaction progresses. So therefore, we say that copper 2 plus has undergone reduction. And in the case of magnesium, it has undergone oxidation because its oxidation number increases from 0 to +2. All right? So this is, as I said before, a very simple example of a redox reaction. And in the next video I'm going to post, there are more complex examples, but the underlying principles are the same. All right? Another thing I want to mention, which I probably should have mentioned before, is the fact that in any redox reaction, the number of electrons lost and gained is going to be the same, right? So as you can see here, in the case of the copper 2 plus, it gained 2 electrons, but in the case of the magnesium, it lost 2 electrons to form the magnesium ion. Okay, so that's what happens in this simple example. So I'm going to stop here. Well, I think there's one more thing I need to talk about. Let me just skip this here and introduce these terms, right? The oxidizing agent and reducing agent. So an oxidizing agent is a substance that causes another substance to be oxidized while it is reduced. And the reducing agent causes another substance to be reduced while it is oxidized, right? So it's kind of like a flipping of the terms, so to speak. So going back to the example I showed you here, in this case, the copper 2 plus would be the would be the reducing agent. So I'm going to put Ra here, right? Copper would be the reducing agent, and the magnesium would be the oxidizing agent, all right? So that's what I'm going to say for now. So the next video I'm going to post will have some examples of redox equations and how you balance them. And that's it. All right, so that's it for now.